If the vector value function is the position vector of a particle moving along a curve, let's say moving along this curve, so then the velocity vector is going to be a vector that in each point will associate the velocity and is calculated as the derivative of the position. So this particular curve, whose codomain is R2, so it's going to be a curve in the plane with two components here. So let's do first a representation of this curve. Remember that to graph the curve, we need to put the parameter t and then the value of x and the value of y. So let's give values to the parameters. So for instance 0, so then cosine of 0 is 1, sine of 0 is 0. So 1, 0 is going to be the first point of the graph. So if we put the x and y axis, so 1, 0 will be the first point of the graph. And if we continue given different values, for instance, pi over 6, and so we calculated how much is the x and y here, and then pi over 4, and we calculate. So we do the whole representation, we will see that this is actually a circle. So this is a curve that we travel in this direction to calculate the velocity. Then we need to calculate the derivative. So the velocity is going to be equal to the derivative of this function, which is the derivative of cosine is minus sine, and the derivative of sine is cosine. So then this is the vector velocity, and we can evaluate, this is the vector velocity for each value of t. And so we can evaluate this vector at different points. So for instance, at the beginning, at 0, what vector is this? Well, it will be minus sine of 0, which is 0, cosine of 0, which is 1. So the vector is 0, 1. So here we are going to have, this is the point where the parameter is equal to 0. The vector is 0 of x, 1 of y, so will be a vertical value like this. This is the velocity vector at 0. And we can calculate, since we have for every t, we can calculate the velocity vector at any point. So for instance, let's say the velocity vector when t is pi over 4, for instance. So let's plug in here pi over 4, and we have minus sine of pi over 4. So that will be minus square root of 2 half, comma cosine of pi over 4, which is square root of 2 over 2. And so then we have that the vector have this component. Square root of 2 is about 1.4, divided by 2 is about 0.7, so it's minus 0.7, positive 0.7. So the vector here So the vector here is the vector minus 0.7. To calculate the acceleration, at t is going to be the derivative of the velocity, the derivative of the one that we just calculated. So the derivative of minus sine of t is going to be minus cosine of t, and the derivative of cosine is minus sine of t. So we have in the same way then the acceleration for all values of t. So for instance, the acceleration for the value 0, that will be minus cosine of 0, this is going to be minus 1, comma sine minus sine of 0, which is 0. So the vector acceleration then will be minus 1, 0 at that point. So let's let's paint here the acceleration vector. That will be a vector like this. So we have the velocity and the acceleration, and we can calculate the acceleration also at any point of the parameter t. So we can calculate also the arc length of a curve that is going to correspond, if this is the curve, the arc length from certain point corresponding to the value t equal a to another point corresponding to the value of the parameter t equal b, that will be simple how long is the curve from this point to that point. And the arc length is calculated as the definite integral of the norm of the velocity. So in order to calculate the arc length, we have to calculate first then the velocity vector. So if we continue with the example of the curve that represents this circle, a curve in the plane which has two components. So the length in this case, let's say we want to calculate the length from t equals 0 to t equal pi 4. I mean this little piece here of how long is this little piece of the curve. Okay, so let's first calculate the velocity that we have already calculated before. We know that the velocity was minus sine of t cosine of t, and then we need to calculate the norm of the velocity. The norm is the square root of the first component square plus the second component square. And so in this case happen to be sine square plus cosine square, which is 1. The square root of 1 is 1. So in this case the velocity is a constant vector. I mean, in this case it's equal to 1. That doesn't depend on t. In general, the norm of the velocity will depend on t. Okay, so in this case, in the particular case of the circle, the velocity is constant. So now let's calculate just the arc length as the integral between 0 and pi over 4 of the norm of the velocity, that in this case is just 1 dt. And so the integral of 1 is t evaluated between 0 and pi 4. This is pi over 4 minus 0. So this is the length of this little piece of the curve, which of course we already knew, considering that this is a circle of radius 1. These vectors in general are different from the velocity and the acceleration, but they are related too. So the tangent vector is just the velocity normalized, and the normal vector is the tangent vector derivative and then normalized. I mean, it's the derivative of this vector and then normalized. Let's consider the curve in the three-dimensional space given by these components t, 3 sine of t, and 3 cosine of t. We can graph this curve in the three-dimensional space, but let's calculate the tangent, the unit tangent vector, and the unit normal vector of this curve. So in order to calculate that, we need first the velocity, right? So we need to calculate the derivative of this function. The derivative of this one will be equal to 1. The derivative of 3 sine is going to be 3 cosine, and the derivative of 3 cosine is going to be minus 3 sine of t. So we have the derivative. Now we need we had velocity, now we need the norm of this vector, right? The norm of the velocity. Well, the norm is going to be the square root of 1 square plus 3 cosine of t square, which is 9 cosine square, plus minus 3 sine of t square, which is 9 sine square of t. So this is the norm of this vector that, taken 9 as a common factor, we get that this is equal to 1 plus 9, which is just 10. Then the unit tangent vector is going to be the velocity divided the norm of the velocity. So in this case it's going to be then 1 over square root of 10, comma 3 cosine of t divided square root of 10, comma minus 3 sine of t divided square root of 10. So this is then the tangent vector. But now, in order to calculate the normal vector, first we need to calculate the derivative of t. So let's calculate the derivative of t. So the derivative of t is going to be, the derivative of this is a number, so the derivative is going to be 0. The derivative of this will be minus 3 over square root of 10 sine, and then the derivative of this will be minus 3 square root of 10 cosine. Okay, and then we need also the norm of this vector, so we calculate the norm of this derivative, that is going to be the square root of this square plus this square plus this square. Well, we'll do all these operations and we get that this is just the square root of 9 over 10, which is 3 over square root of 10. Okay, so then the normal vector is going to be equal to t prime, which is this one, divided by its norm. So then it's going to be equal to 0 minus sine of t, since these two cancel, and comma minus cosine of t. Okay, so this is the way then to calculate the unit tangent vector and the unit normal vector. So we see that in this case we have the particularity that the derivative is also constant here, so that makes things easier. In general, this derivative is not going to be constant, and then you will need to do a derivative that is much more involved. So for instance, let's consider, and because we will be tempted here to think that this is essentially just the velocity, right? And this is essentially just the acceleration. Well, it's not. So in here, even though it is essentially the velocity just normalized, this one is not essentially the acceleration, because the derivative that we are calculating here is the derivative of the tangent vector, and the tangent vector can get very complicated when the norm is actually depending on t. So let's see, for instance, this example. So if we have the example that this is a curve, just 2 dimensions, given by this vector as position vector. If we calculate the velocity, this is just the derivative, so it will be 2 to t. And then we calculate the acceleration, the derivative of 2 is 0, the derivative of 2t is 2, so the acceleration is very simple. But let's see what happened when we calculated actually t and n, the tangent and normal vectors. Well, first we need the velocity, the norm of the velocity. But see that here the velocity depends on t, and the norm is also going to depend on t. It's not going to happen like in the other cases that t was cancelled. So here we have a velocity that depends on t. And so when we do the division of these two things, we get that the tangent vector is equal to that. And so now we have to do the derivative of this. And you see how different is to do the derivative of this, how different it's going to be from the acceleration, because this derivative is going to be very involved, right? We have a quotient, we have a square root. Well, you should do all the operations here, and the derivative of the tangent should be what we get here. And in order to calculate the normal vector, we need to calculate the norm of this vector. Well, we do the square root of the square of each of the components, we simplify, and we get this. This is actually the norm of the tangent vector. And now we need to divide this divided by this, and that is what will give us the normal vector. That, as you can see, is very different from the acceleration. Well, the curvature of a curve RT is defined as the scalar function. I mean, it's a function that is going to assign a number to each t. It's not a vector value function, and is the derivative of this vector, the vector tangent that we were talking about, the norm of that divided the norm of the velocity. And this is the same that doing actually the cross product of the velocity and the acceleration, calculate the norm and divided by the norm of vq. So depending on the data that you have in the problem, you will find that it's easier to calculate the curvature in one way or the other. So for instance, if we have already calculated, like in the previous case, the derivative, the norm of the norm of the derivative of t and the norm of the velocity, so then it's just a quotient of these two things. So in the previous example, for instance, we have calculated here the norm of the derivative of t, and we have calculated the norm of v. So the curvature will be just the quotient of these two things. In the previous example, though, in which we have a curve in which the velocity was constant, so we're going to have here that we also have the norm of the velocity and we have the norm of the derivative of t. So just the division of these two is going to be the curvature of here. So the curvature will be equal to divided the norm of v, which is this. So the curvature is 3/10, the curvature of this curve. As we have said before, the acceleration is not necessarily in the same direction of the normal vector. In fact, the acceleration can be written as a linear combination of the tangent and normal vectors. And the way to calculate the coefficients in this combination is given by these formulas. The coefficient that we have to multiply here to the tangent vector is the derivative of the norm of the velocity. And the component here, the coefficient multiplying the normal vector, is the curvature multiplied by the norm of the velocity squared. So, for instance, let's consider a new curve R, depending on t, equals to t squared over 2 plus 1. That's the first component. The second component is going to be t squared plus t minus 2. And the third component is going to be t cubed minus t plus 3. So we have a curve then in the three-dimensional space given by these equations. So now we want to calculate the decomposition of the acceleration into the tangent and normal vector. For that, observe that both coefficients depend on the velocity. So in fact, depend on the norm of the velocity. So the first thing that we need to do is to actually calculate the velocity and then calculate the norm. Okay, so the velocity is just the derivative of that, right? So the velocity is going to be equal to, and so we do the derivative of this. Well, the derivative of t squared over 2 is just t. The derivative of 1 is 0. So the derivative of t squared is going to be 2t plus the derivative of t is going to be 1, and the derivative of a number is 0, comma, and so the derivative here is going to be 3t squared, and so here minus 1. Okay, so this is the velocity, and now the norm, and this is r prime, or velocity, and now the norm of the velocity is just the norm of this vector. So the norm of the velocity is going to be equal to square root of, and so we do the square of t plus 2t plus 1 squared plus 3t squared minus 1 squared. So the square root of all that. So we expand all these squares, and this is going to be equal to the square root, we combine like terms, 9t to the fourth power minus t squared plus 4t plus 2. So 80 then is going to be equal to the derivative of this. That is 1 divided 2 times the whole square root times, by chain rule, the derivative of whatever is inside. So in this case is 36t cubed minus 2t plus 4. And so simplifying, we get that 80 is equal to, dividing everything by 2, we got that this is equal to 18 t cubed minus t plus 2 divided the whole square root, the square root of 9 t to the fourth minus t squared plus 4t plus 2. So this is then the component that will be multiplying by the tangent vector. To calculate the normal component, we need to calculate the curvature. Let's recall how the calculation of the curvature. For the curvature, we can either do the derivative of the tangent vector, the norm, and divide by the norm of b, or we can do this other alternative here. So this is the velocity. I think that the velocity cross product with the acceleration will be the best of the path here. So we're going to do this. Calculate v times the acceleration divided by the norm of v. Recall that v is this one, so the acceleration, that is the derivative of this, will be equal to 1, 2, 60. So that's the acceleration. And now we need to multiply cross product the velocity and the acceleration. And so this is done by taking the determinant here, a I, j, k, then the components of b that are going to be t, 2t plus 1, 3t squared minus 1, and the components of the acceleration, which are 1, 2, 60. We do this determinant, and we get that this is times e minus 3t squared plus 1 in the second component and minus just 1. Okay. So this is the cross product, and then we need to calculate the norm of the cross product, of this cross product. So the norm of this vector is going to be the square root of, and we do this square plus 1 squared. So the result of this to the fourth power plus 72 t cubed plus 66 t squared plus 24t plus 6. Okay, so this is the absolute value of the cross product. And so the two things that we need to calculate the curvature are this and this, right? So the norm of the actual vector b. So let me remind you that the curvature is equal to the absolute value of b times a divided b cubed. And so when we have to multiply here, we are going to have to multiply by b squared. So at the end of the day, so here we are going to get just an equals k, which is this index which is wrote here, divided b cubed times b squared. So at the end of the day, this is going to cancel with this, and we're going to get just b times a divided by b, which is just this divided by this. So this is the final result then of the a. Vector here can be written as something multiplied by t, and this something is this, and something multiplied by n, and this something is this. So we did find what are the two coefficients on the linear combination. Finally, these two vectors, tangent and normal, are two perpendicular vectors, are both unit vectors. So the cross product of them is going to be called the binormal vector, and this is also a vector that has magnitude 1. And the three vectors together form an orthonormal basis of the three-dimensional space. In fact, it's a basis at each point of the curve. I mean, if we have given any curve, at each point of the curve, we are going to have a basis there formed by the tangent vector, the normal vector, and the binormal vector. So let's see how this looks like. So we have here represented this curve in black, the curve given by this equation, cosine t, sine t, t, this is a helix, and so we can see this curve in different ways. And we have given in this particular parameter t, we have painted here, we have represented here the three vectors in the Frenet frame. So these vectors are in green, the tangent vector, in red is the normal vector, and in blue we have the binormal vector. And in each other value of t, let me change. So for instance, at the beginning, that's where the Frenet frame is, so I change to another value here. So we can see that at this other value of t, where these three vectors are. So we can consider some other one here, so we see how this, in different values of t, we can see the representation of the Frenet